Hello and welcome to Math with Lou. Today we are going to be talking about the numbers. When we refer to numbers in mathematics, there are a lot of different things we can be talking about. So we're going to go over each and every one of those things. We're going to start very small and expand outward into our different sets of numbers. So the first set of numbers that we can talk about are known as the natural numbers, or the naturals. This n with two lines going two diagonals is our symbol for the naturals. And a nice informal definition that we can give the naturals are numbers that occur in nature or naturally, hence the name. A better definition would probably be positive whole numbers, but they're called naturals again for the reason that they occur naturally. You have one apple. Technically, you could have half of an apple, but that half of an object that you still have is one object. Something of controversy among mathematicians in regards to the natural numbers is 0 a natural number? Many argue for it to be one. Many argue against it. Technically, you can have 0 something, but technically you can also not have 0 something. So personally, I don't like to think of 0 as a natural number. I don't think you can have 0 of something, but apparently that's up to personal preference. Every textbook is a different definition on that one. Expanding out from the natural numbers, we now have the integers, which the symbol is this Z-looking thing with two diagonals. This one I happen to know why the symbol is a Z. A good friend of mine from college shared this with me. The German word for integer, I have no idea what it is, and God forbid I try to pronounce it. That word begins with the letter Z. And I'm assuming that the mathematician who dubbed term integers, he got the credit for it. So they gave it the German letter Z for the German word for integers. An integer is defined as a whole number, positive and negative. And this also definitely includes the number 0. So here below, I listed the entire set of integers from negative infinity, negative 3, 2, 1, 0, 1, 2, 3, up through infinity. Again, they are whole numbers, positive and negative, can be 0. Expanding our definition of numbers even further, we now get to the rationals, which is this symbol Q here. No idea why it's a Q. But a rational number is defined as two integers, which we typically denote P and Q, that can be expressed as a fraction P over Q with Q not equal to 0. As we all know, can't divide by 0. So here are some examples of some rational numbers. This is not all of them, but a handful. 7 over 11, two integers dividing each other. Negative 2/3, two integers dividing each other. 5, well, now this is not a fraction. This 5 can actually be expressed as a fraction. We can call it 5 over 1, which now it is a fraction. 0, we can call this 0 over any number. We can express this as a fraction. 1.33 repeated. Now, this doesn't look like a fraction, but we can express this as a fraction. This number is nothing more than 1 plus 1/3, or 4/3, which now, voila, we have this as a fraction. Expanding out from the rationals, we now have the irrational numbers. While I was getting ready for this video, I found this symbol P for the irrationals. In looking into this video, I found that this is a very uncommon symbol. Typically, the irrationals are denoted as the reals minus the rationals. I didn't want to write it like that. I like having one symbol for each definition. So I'm going to go with this P thing here. So an irrational number is a number that is defined as a number that cannot be expressed as the ratio of two integers, or in other words, it cannot be expressed as a fraction of two integers. And here are some examples of some irrational numbers. The square root of 2 is irrational. There's a very elegant proof as to why this is irrational. Hopefully one day I can get around to a video putting that proof together. It's pretty cool, but square root of 2 is irrational. Pi, we all know the most famous number in mathematics, pi, 3.14, goes on for infinity. It never repeats at any point, cannot be expressed as a fraction. The number E, Euler's number, very famous in physics too, but I was going to say calculus, introduced to it in pre-calc. And the number phi, which is the golden ratio, which My favorite thing about this number is some of the digits make up my birthday. But all of these numbers, the one thing they have in common, cannot be expressed as fractions, and the decimal digits will continue on for infinity with no repeating pattern at any point in that infinite abyss of numbers. Next, we get to the reals, the real number. And the real numbers are pretty much every number that we've talked about so far. All of these numbers together make the reals. Real numbers are numbers that can be represented on a number line. Now, the number line is it's so funny because it seems so childish to refer it back to number lines. You associate this with kindergarten, first grade math. But the number line can be very, very, very useful tool when talking about numbers. And the way we visualize the number line, I'll draw a quick little picture over here. Here's our number line. And I'm just going to do the numbers between 5 and 5. Negative 5 and 5, I meant to say. Now, we can express every single one of these numbers on here by drawing a thick red line between our two numbers on our number line here. I have just expressed every single number, all of the infinite amount of numbers between negative 5 and 5, just with this very simple line here on my number line. So, very simply put, the real numbers are all of these. They're all the numbers. But that begs the question, well, wait, there's still one more. How could we talk about one more if all of these make up the numbers? And because now we talk about the complex numbers, which involve the imaginary number I. So what's funny about these, well, let's go into the definition first. The complex numbers, a number that can be expressed as a plus b I, where a and b are elements of the reals, so a and b are all of these numbers, and I is the imaginary number defined as I equals the square root of negative 1. Up until Algebra II, students are taught that you cannot take the square root of a negative number, that it's impossible, that there is no number a times a that equals a negative. That is impossible. We can't do this. Well, it turns out that even though we can't technically do this, this imaginary number I is insanely useful in lots of fields of upper mathematics. If you're familiar with Euler's equation, what is it? E to the I pi plus 0 equals 1. Super elegant and beautiful right there. I'm no video game designer, but from what I understand, the imaginary number comes up a lot in video game design. But anywho, these are numbers that relate to I being the square root of negative 1. And here are some examples. I, 6i, 2 plus 3i, all examples of imaginary numbers. And the last thing that I want to talk about, I put it down over here. All of these groups are subsets of the following one. So, meaning, the natural numbers, they are integers. The integers and the natural numbers are rational numbers. The naturals, integers, and rationals are also irrationals. Naturals, integers, rationals, and irrationals also make up the reals. And then all 5 of these are part of the group of the complex numbers. But it does not work backwards. I cannot say that complex numbers are real numbers. I can't say that complex numbers are irrational numbers, but I can say that irrational and real numbers are also complex numbers. And I can show that very easily if I just, for right here, if I define my b to be 0, so if I say, 3 plus 0i, well, this is 3, and we know that's an integer. So we just showed very easily how an integer can be part of the group of complex numbers. So these symbols down here, these C-looking things with a line under it, this just means subset. Just go through it one more time. Natural numbers are subsets of the integers, which are subsets of the rationals, which are subsets of the irrationals, which are subsets of the reals, which are subsets of the complex numbers. This is all I want to talk about today in today's video. Just wanted to go through definitions of the numbers. I hope you enjoyed today's video, and thank you for watching. Hope to see you next time.